So today we're going to talk about atomic structure and ionic compounds and how these relate to valence electrons, valence electron cells. So first let's talk about the structure of it. Now atoms are 3D things, so they exist in a 3D space. So I'm going to do my best to draw it in 2D if you understand. This is how you'll see it drawn in pictures on your textbooks or on the board or on the AP test, but you need to understand this does exist in a 3D space. And that's important when you go to how atoms combine and the structures they make when they come together and things like that. So just remember, although we're going to do everything in 2D, these are 3D things in 3D space. So in an atom, there are two main parts. There's the center, which is the nucleus, and there are these outer electron rings. And they exist around the atom like this. Now, when you see it depicted on your textbook, you'll see a tight little nucleus, and then you'll see these rings with, oh, I'll draw that in a different color, I'm sorry. You'll see these rings with electrons dotted on them. And it's going to look something like this. Now, your chemistry teachers and your college professors, or wherever you're learning this, they might try to teach you the history about like how we got the atom to be where it is today and how we came up with how it looks. And I'm just going to tell you flat out, as soon as they test you on that, you should forget all that knowledge because it's absolutely useless to the AP test. It's absolutely useless to a future chemical career. If you're interested in chemistry and you want to know it, then you should, you can learn it. And so I'm not saying you shouldn't learn anything, but just know it's pretty much useless for the point of getting an A. And the whole point is should be getting an A, getting a 5 in the least amount possible, and retaining the knowledge you need to get those grades. So they may tell you about farm model or models like this, and you should forget about it. The only thing you should really remember is how atoms actually are made up, not the progression to get to where they're made to the model we have today. So, so in the middle here, we have the nucleus, and this is where all the mass, all the gravity, the protons and neutrons are existing. And then on these outer shells here, we have electron. We call these electron shells. And in these shells is where our electrons exist. Now remember, they do exist in a 3D space, not a 2D space, but for the point of displaying, we're going to show them 2Ds. So within an electron, or sorry, within an atom, there are different electron shells. There are the electron shells on the inside, and we call, oh, I should not use that color, I'm sorry. And we call these the core electrons, with the core electron shells. And then these on the outside are the valence electrons, or the valence electron shell. So in my next video, I'm going to detail periodic trends or trends that you can generalize to all elements, no matter how they act, based on where they sit on the periodic table because they're grouped. And it's important to understand the difference between core electrons and valence electrons, or something called effective nuclear charge. And basically what that is in this middle right here, you have your protons, and your protons exert a positive charge. So they have a positive charge. In the electron shells, your electrons, which a lot of times you'll see it written right here as E minus, these exhibit a negative charge. Neutrons are neutral. That's in the name. When you see the word neutrons, you should think neutral. So they don't, well, no, I'm sorry. They don't exhibit either a positive or negative. They're just useless. They're just there to add to the mass of the atom and make up the isotope. So the protons have their positive charge streaming out from the nucleus. Their positive charges are going in, while the electrons have their negative charge pushing in against the positive charge, working against it. These electron charges also work against each other, and this is something called electron-electron repulsion, where electrons are actually repelling each other very slightly. This is very small, but it does add a little bit when we get into different geometries. So it's important to know electrons do repel each other a little bit, but they mainly repulse against the center protons, and that's why they exist in these shells. So the protons have a pole. So in the middle, they have a pole, and if there's two protons in the middle, So helium has two protons in the middle, has a 2 plus charge. And this outer ring, or this core electron shell, so the first ring, is being exhibited to a 2 plus charge on it. And it's pulling this in with a 2 plus charge, as you can see here. But if you have a much larger atom with, let's say, 20 protons in the middle, this inner shell right here, this core, oh, that's a big blue, I'm sorry. This core shell right here is being exhibited on by a much stronger pull because there's 20 of these plus poles pulling it in, meaning this electron shell exists closer to the nucleus, even though there's still the same amount of electron repulsion because there's more plus pull, the electron shell will exist closer to the nucleus. Now, this is very important when you think about core and valence electrons. So because valence electrons exist in the very outer shell, this changes per atom, as different atoms have a different number of electron shells. And you'll see this as you go down the periodic table. Group 1, or row 1 of the periodic table, has one electron shell, and then row 2, the periodic table has two electron shells, and row 3 has three electron shells, and so forth. And the valence electron shell is the outermost electron shell. So it's important to make this distinction when you're um, dissecting or describing or looking at an atom, because the valence electron shells are different per atom. So when we say valence, we just mean the outermost electron shell and the outermost electrons. So on the periodic table, you will see, we're going to use lithium as my favorite example because it's simple, easy, and it lets me keep a lot of things. So we have lithium, and lithium, I'm not going to worry about molar mass for now because it's not important to this. Lithium has three protons in it, and it exists in the second row. It's the first one in the second row. So it exists in the first column, so represent the first column, and it exists in the second row. And it has three protons, so it's 3 plus charge being exhibited from the nucleus. So if we draw lithium, we have our center nucleus, and then we have our outer ring 1. The first outer ring holds 2 electrons, and every other ring after that always holds 8. So the first electron shell always holds 2, and the next one always holds 8. And the electrons will fill up the electron shell in the order as they move out. So lithium has 3 protons, and in an atom state, it has neither a positive nor electric charge being exhibited from it. So it must have the same number of electrons to cancel out this 3 positive charge right here. So it must also have 3 negative charge electrons to cancel out so that we have 0 charge. So when you see stuff on a periodic table, it's existing in its atom state, where it has the same number of electrons to protons. Unfortunately, in the real world, atoms like to move around a lot, or sorry, electrons like to move around a lot. They like to leave their atoms. They're not bound like the nucleus is. The nucleus is bound together. Electrons are. So when you exist in the first column, this is a column that's highly reactive, and it is highly reactive because this electron right here that's existing in the outer shell, the only one, is getting a very weak +1 charge exhibited on it because the other +2 charges are repelled by this electron. Not only that, it's also farther away than other electrons would be because it has this weaker charge pulling on it. So it makes it really easy for this electron to just leave the electron shell and leave the atom altogether. And when this happens, when this electron leaves, lithium now has one less negative charge to it. So lithium actually has a positive charge. We have a positive charged lithium atom right here. But we don't call this an atom. We would now call this an ion. And we call this an ion because it doesn't have a valence electron shell. Once this electron here leaves the shell, this shell is completely gone. It doesn't exist. A shell isn't a physical thing. It's just space that an electron takes up while it orbits the nucleus. Because this is gone, there are no more valence electrons. And we just have these core electrons. And that's how we know we've made an ion. And an ion is kind of how atoms, or I should say elements, like to exist. They like to exist in ions because they're much more stable and they don't have these really weak electrons trying to leave them. So this is important to know that this is what we mean when we have an ion. It's when it has no more valence electrons. Now, ions obviously change as you move across the row, because if I was over at beryllium, which has 4 protons, we know that this has a +4 charge in the center, but it still only has 2 core electrons. So the ion for beryllium is a 2+ charge ion. This is important distinction to know as it's going to be important for everything you do in chemistry. So just know an ion is a element that has only core electrons, and the valence electrons are now no longer their electrons. This can also exist in another one where, let's say, oxygen exists. Oh, that's a terrible one. I'm so sorry. Oxygen exists, and oxygen is 16, 8. Oxygen is 8. I'm sorry. Oxygen is 8 protons. So this means it has a +8 charge in the nucleus. Now, just like every other atom, it's going to have 2 center electrons. So we have 8 plus charges in the nucleus and 2 electron minus charges in the outer shell, and then 6 electron minus charges in the valence electron. Actually, I meant to say core here. Let me label this. Let me change my color, please. So this would be my core electrons. And these are my valence because they exist in the outermost shell. Now, in order for oxygen to be an atom, to be an ion, it could lose all 6 of these electrons. Or, what makes more sense, because it already has 6, it's going to want to gain 2 more electrons from somewhere else. So it wants to get these somewhere else so it can fill up this valence electron shell, and then this valence electron shell will become a core shell because it is completely full. So it's going to get these by bonding to an atom like beryllium, where beryllium wants to give away 2 electrons, and oxygen wants 2 electrons. So when it makes this bond, oxygen will have it still have 8 protons within the nucleus, but now it'll have 10. 2 here, 6 that it already had in the valence, and then 2 more it gets, and it'll have 10 electrons in total. And that means the 8 positive charges will be canceled out, and oxygen will have a -2 charge, and it'll exist like this. This is important to realize that when you have a periodic table, on the left side of the periodic table, this is going to be a terrible drawing of the periodic table, just bear with me. On the left side of the periodic table, you're going to have ions that are positively charged, and on the right side of the periodic table, you have ions that are negatively charged. In the middle here are your transition metals, and we're going to talk about this in a different video where I talk about periodic trends. Hopefully you guys understand now how an atom is made up and what an ionic compound is. So just remember, the atom structure has its protons and neutrons in the center, in the nucleus, and it has valence electrons and core electrons floating around it. Once the valence electrons represents the outermost incomplete shell. Once that shell is filled up or disappears, that atom now becomes an ion. And ions is really what we see in real life, as atoms like to gain and lose their electrons to be more stable elements.